Okay, a very good morning. So can everybody hear me? If you can hear me, please react to something or maybe show hands. Okay, good. So welcome everybody to our deep learning image classification with Keras workshop. So this is our first workshop. So please bear with me if it's not up to your standard. So we're just trying it out, and then we hope that you can learn something from this workshop. So first and foremost, if you guys could just download the Python notebook from the chat. If anybody has any problems, please do show of hands. So does anybody have any problem with trying to upload this into their own drive or adding it to their drive? You can add it to your drive using this function. Save a copy in drive. And you add a copy into your drive and you can edit from there. So is there any problem? I hope that you guys have a basic understanding on deep learning, AI, and all those stuff. So if you want to do it, you can maybe open up your Google Collaboratory and then do this with us. So it's easier for you to get on, and you can edit this thing if it's in your own Google Drive. So to edit the text part, you just double click it and then you can edit it. So whereas for the coding parts, you can just type it in and then it's corrected then already. So yeah. So let's go through this thing. So we're using Google Collaboratory. So it's like Jupyter Notebook. So this thing is actually developed by Google, and then you can do your Python coding online, and then it's free for 8 hours at one time. That means you can run for a total of 8 hours. Then Google will prompt you, like when you're watching YouTube videos, you don't touch your laptop for a long time. Afterwards, they will show a pop-up video saying, "Are you still watching me?" Then you have to press yes, right? Then you continue the video. So this is exactly the same as Google Collaboratory, but it's 8 hours. So you let it run for 8 hours. Then after that, you'll start asking you, "Are you still there? Are you leaving me alone?" Or something like that. Then you just press yes, and then you continue running the code. So Google Collaboratory is used because it has external GPUs that you can use. Let's say your computer is not really up to snuff with the GPU. So actually you can use Google Collaboratory. And then you have about, if I'm not wrong, about 13 gigs of RAM and then 100 gigs of disk. So actually it's quite a big chunk of hardware there that you can use if your personal computer is not up to snuff. So let's start with differences between AI, ML, and DL. So AI is artificial intelligence, ML is machine learning, and DL is deep learning. So you can look at this graph, you can see that ML is actually a sub of AI, and then DL is a sub of ML. So that means DL is a sub of AI. So let's give an example. So like chess, you set the rules for it, and then depending where the chess pieces are, it performs certain duties for AI. Whereas for ML, you give the program the steps of how the play was played, and then the program will run through it and then find the rules from it. But for deep learning, they have more layers in between, and then you convert the data to another form, performing it much better, and then you'll form a better output. So it'll be a more precise rule that is done compared to ML. And then next we will go through Keras. So Keras is an API for TensorFlow. TensorFlow is being, how to say, it's maintained by Google. So this is their TensorFlow is Google's part of creating a library where people can make their own algorithms for machine learning, deep learning, or AI. So and then Keras is here because it can simplify the coding that is from TensorFlow. So it's a wrapper for TensorFlow. It really simplifies it down, so it's very easy to program as compared to TensorFlow. So actually, TensorFlow has a mini major upgrade recently, which is it's called TensorFlow 2.0. Compared to TensorFlow 1.0, which is the older version of TensorFlow, TensorFlow 1.0 is very thorough in the steps. So you need to program like literally every single part, like one layer, what layer you want to use, and then what type of you have to really specify every single thing, and it makes the coding very lengthy and then very hard to control. So TensorFlow 2.0 is shortened, and then Keras is a wrapper that makes it much easier as compared to TensorFlow 2.0. But you can interchange both of them in the same code. It's usable. So TensorFlow can be used for image classification, data clustering, regression, reinforcement learning, natural language processing. So image classification is what we're going to be doing today, which is classify images. Data clustering is like when you want to cluster all the data together, like let's say people from the red team or such. That is what you can use. Regression is usually used in for places where you need graphs. Actually, all of these use graphs, but regression is like for economics. You want to see how much the price you can go, how high can you go before you start losing money or people don't want to buy it. Reinforcement learning is just another form of making sure that the program can run better in a way. And then natural language processing is just now what the video said, RNN. So it's used for like your Grammarly, your word, everything, all those grammar mistakes, they all use natural language processing. Like Google Translate, it has a lot of natural language processing inside. So now we'll go on with the next subchapter, neural networks. So this is a shallow neural network, whereas this is a deep neural network. So as you can see, there's a difference between both of them. And then the only difference is the amount of hidden layers in between. So a shallow neural network is normally about 1 to 2, maybe maximum 5. Whereas a deep neural network, although this is a simplified version, it only has 3 hidden layers, but actually you can go all the way to a few hundreds for a few, or even the most, one of the more modern architectures, right? They use about a few hundreds of them in between. So it's part of it that makes it much better at computing the accuracy when it comes out. So is that, and then now I'll go on with the mathematics. I know this is still a bit boring. I know it's early in the morning on a Saturday, so just bear with me. I'll go on quite fast with this, then we can reach the coding faster. So as you can see from here, right, y is here. So f is the function. So summation of n is the number of neurons, and then I means this typical programming start from 0 and then go all the way from bottom to the top. And then this is the weightage. So weightage is calculated by the algorithm itself. So how much weightage do they want to put on each neuron for extracting features? And xi is the number of input or the number of neuron at that time, plus a b. This is the bias. So this weightage and bias is actually calculated by the program during backward propagation. So this is the big explanation, but I'm lazy to go through, and then I know it's in the morning, it's very boring. It's Saturday some more. Okay, so now we'll jump in straight into deep computer vision. So we'll be using convolutional neural networks or CONVNets or CNNs. These are all interchangeable. So we want to identify and classify images. So we need to know the important concepts such as image data, convolutional layer, pooling layers, and architectures from CNN. So image data is split into 3 parts because everything in algorithms, right, there are a lot of dimensions. So for images, normally there are 3 dimensions if you're using RGB. So first is the image height and image width, which I'm sure all of you are quite familiar with. Like we take our Instagram photos, we know that the image height and the image width has to be the same, or else you have to zoom out or it won't look as nice. But although I know some people, they like to put a blank space in between, so that does not affect them. But if you're in the very olden days of Instagram where you're forced to make a square photo, yeah, image height equals to image width. And then color channels is depending on the type of camera that you're using. So normally you'll be using RGB cameras, so red, green, blue. this is the typical colors that we'll be using for our camera. So each channel only can hold one type of color. So if you're using RGB cameras, right, you have 3 channels. One of them is for red, like here, green, and then blue. So as you can see in this picture, so let's say for this one, right, it's a 4x4. So this is a 8 pixel, 3 color channels. And then for the color channels, right, they run for each block inside here. It runs from a value of 0 to 255. Why is it 0 to 255? Because in programming or in digital electronics, there's a value. We always start from the value of 0, then we run all the way up to 255. So that means there are 256 values. So that means it is 8 bits, if I'm not wrong. Yeah, it's an 8-bit, so that means it's a byte. So that means each photo is a byte. So that means this is 4 times 4 is 16 bytes times 3. So 16 times 3 is a 48 byte photo for just a 4 times 4 pixel for RGB. So now we'll go into CNNs. So CNNs consist of a few types of layers. So there's convolutional layers, dense layers, pooling layers. Yeah, these are the main 3. So now let's go through what type of layer does what. So let's say a convolutional layer versus a dense layer. So convolutional layers, right, they look at the region itself. So like we see this photo. I'm going to zoom out first. You see this photo, and then you're going to look at, for us humans, we're going to look at the whole thing. Then we say, oh, this is a cat. Whereas for computers, right, we're doing in DLs now. So for convolutional layers, they'll look at this small part. Oh, so this is what makes up an ear. So maybe like this line over here plus a little bit hairs here. This makes up an ear. An eye is just a round with another slit in between. A nose is something like this. So this is what convolutional neural networks, convolutional layers look for. Look at the small regions in the whole picture. Whereas for dense layers, right? Oh, sorry. As you can see down here, this is what a convolutional layer will look for, like ears, eyes, nose, maybe these paws. As you can see, there are a few lines over here. If you strain your eyes. So yeah, this is what convolutional layers look for. Whereas for dense layers, right, you just look at the entire image. And then you see, oh, so this is what a cat looks like. But you only can memorize it like if the cat head is over here. So once you just flip it on its axis, right? Let's say the head is from here now. You just flip it to here. The dense layer will totally go KO already. You won't understand that it's a cat. Whereas for convolutional layer, it still look for the same features like the ear is over here, the eyes will be here. So you can still recognize it as a cat. So we are using dense layers and convolutional layers to like get the whole output out. Okay, so these are a few more examples. This one I suggest maybe if you guys really want to look into it, you can read through it, but due to timing, we will like go through it quite fast, all these theoretical parts. So the most basic one, we're going to start it afterwards, a convolution CNN with 3 layers. So now we will go through with more technical stuff first. So there are a lot of other parts that you need to tick off. So like feature maps, activation maps. So let's say you just actually for long story short, you just look at this TLDR in this part. So sorry. Sorry, where was I? Okay, so you just look at the TLDR, and then what does this mean? It just looks at the output filter of a CNN. But why do we want to do it? We just want to check the filters. So filters is what a convolutional layer look for. So let's say from this example, this is a 0 that we can see, right? So from this 0, you apply a filter. Let's say this filter looks for a slanting diagonal, and then you output this layer. So you can see for us it becomes blur, but to the computer, if there is this layer and then a few more here, then this can form a 0. So this is how machine learning looks for. Okay. So now we go into even more technical stuff. I know it's boring, just please bear with me. So sample size is how big is your, sorry, sample size is how big the filter needs to be, and then borders and padding. So let's say this is your image in gray, and then this is your padding. So when we are slide for convolutional layers, right, with this filter, you usually slide over these few parts. So if you're just taking the original image, let's say we're taking a 2x2 filter, so you only show this box, and then you'll slide over here, and then slide over here, and slide over here. So that means you only have 4 outputs. But that means that this block, this pixel, and this pixel, and this pixel, and this pixel will not really get to show their values. So we normally add a padding around it so that you can show their values as well. So they're in the middle, because normally for a filter, we will put the most emphasis in the middle of the filter. So that's the whole thing. So strides, common, but we don't really use it in this one, so we just talk about it. So pooling. So as you know, our images nowadays are in the megapixel range, so it's very big. So normally we will shrink it down into about more manageable, like 500 pixels in total. Then we'll just shrink it even more. So from, let's say, 500 pixels from an image, how do we get an output? So although dense layers and convolutional layers do shrink it down, but we use pooling layers to shrink it even more and much faster. So pooling, there are a few more types, and then we'll talk about it later. So layers, there's input layer and output layer and hidden layers, as you can see from the top over here. So let's just scroll up here. So this is the input layer, hidden layers, and output layers. So output layers is where you get your prediction from. Okay, so now talk about neurons. So neurons is something like, just now the video said, so neurons is something like your neuron in your brain. We're trying to apply it in real life, sort of, in our this programming. So we just want to mimic humans or maybe brains here. So yeah. And then connected layers, we need to connect all the neurons together, or else they will not be connected. So like, let's say, you know, those baby formula videos, all of them just drink the baby milk, and then suddenly the neurons all connect to each other. Yeah, so this is something around that line. So weights, all connections, right, they must have a weight, so they can show how important their connections are to the next input. So because we want to reduce the amount of data in the end, so that means the whole model must know that, okay, by what time this is important, by what time this is not important. So this is the weightage and biases function. Activation function is how much the neuron. So I'll go into a bit technical in bio currently. So neurons, right, they have a threshold. Let's say, I cannot say voltage. There's a region where after that is stimulated. I don't remember the correct term for now, I'm sorry. But neurons, right, they work by having enough stimulation. Then after that, after a certain limit, they will stimulate itself, and then it will send out a new pulse. So this is what we're trying to do, but in programming. So the most popular one is called a ReLU function. It's a rectified linear unit. So you can see from the graphs down here, you can use different types of activation. It will produce different types of models for you. So backpropagation is very important because in deep learning, right, we are going to send in an image, and then you will try to understand the image, and then you'll predict a function, and then you'll check with the correct output, which we'll give it also. Then it will go back and then change all of the weights of the biases, and then make sure that that output that it has calculated is the output that we want. So this is very important for us. So loss or cost function is because we want to just now I just said, we want to give up on some of the data that we don't use, because overwhelming the computer, right, you just slow it down. So there are a few types of losses here, and then gradient descent is just how the computer calculates what is the value that it's supposed to be, so that you can get the best output. So we will normally find the lowest part of the graph. So let's say this is our output, right? This is the weights and biases. So let's say we start from here. We want to go down all the way to the lowest part. So this is like the safe zone for it. So normally there are a few reasons. Like down here you can see there are about 3 regions where it's the lowest part. So normally you want to get it to the lowest here, but sometimes it goes to here, and then we need to find a way to like push it back up here and then let it flow down here instead. So optimizers. So this one we don't really use it, but yeah, optimizers is just to how to change this in a way. So yeah, actually you can just go on with this link when you're done after this workshop. You go through this link, actually will explain much more thoroughly as compared to what I'm doing currently, because there's a lot of coding to go through afterwards. So now we'll start with the coding after this. So you need to know there's 3 different types of data: training data, validation data, and testing data. So training data is what we have with the original images. So normally we'll put in another type of data for it called label data. So there's image and there's label. So labeling is like a caption for the image. So you want to put in these 2, and then you'll check, you'll look at the image, try to get an output, and then see the output is the same as your label. Then you'll back propagation, and then you'll edit everything. And then validation data is just to we give another type of data, a new data that is not the training data, it's a different data, and then it will go on change. It will just do a slight tweaking of the model so to make sure that it's better as compared to just pure training. And then testing data is like when you're going to apply this model in real life. Let's say we're doing something about checking for coronavirus. So we gave it a lot of old viruses like SARS in the olden days. So for like training and validation, we just gave it SARS, H1N1, H5N1, all those type of viruses and the mutations. And then now we want to do it on current ones. So let's say we want to detect how much the new coronavirus can like mutate. So this will be the testing data. So fun fact is that this tree has to be 3 different data, and then for the whole training of the whole model, the model must not be able to see any testing data. So this is to make sure that the computer does not memorize that data, because computers, right, they are good at memorizing. So once you let them see the image one time, they'll remember it for the rest of the time, so long it's in their data set. So we don't want it to see any data, any testing data, because once you see it once, they'll memorize it, and then it's no more useful for the whole thing. So now we can start with the testing, the coding. So I'm sure here you see that I've already connected. Okay. So you can see that I've already connected. So you just press connect and then wait for it to load first. Then you can run the code over here. So let's start with some coding. So we'll import TensorFlow from Keras. From TensorFlow, you import Keras. These are all in Python. So if you don't understand Python, maybe you'll find it a bit tough. But if you understand Python, I'm sure this will be very easy for you. Just importing libraries here, there. So NumPy and then Matplotlib. So we're going to be plotting graphs, so we'll be using this function, whereas NumPy will be using for calculation, and then Keras and TensorFlow will be used for the whole program. So if you run this code, right, you see that it prints hello world. This is my version because I added in already. Another fun thing about this type of notebooks is that you can run this code, then run the bottom one, and then let's say you want to do a change, right? You can run back this one, and then you can change it to the next one. Let's say that this is just a function that you predefine by yourself, and you don't need to keep running it, because normally we use the Python IDE, right? Or let's say code or Visual Studio, you must run the whole code. Whereas for notebooks, right, you don't need, so long as it's run once and there's no edit to it, you can just leave it there and then run other slides of codes. So I'll be using, for this data, for this parts, we'll be using the Minis fashion dataset. So Minis is actually a competition for image classification So this dataset has 60,000 images for training and 10,000 images for testing. So let's load the dataset into our variable here. So we just run this. As you can see that we're going to load the data separately. So once it loads the data here, we'll take it out, and then we'll put into train images, train labels, test images, and test labels. So once you run it, you just download it from Google, and you can see over here in your folder. So let me change. I'm sorry, the download is taking some time. Okay, so as you guys can see, right? So this is the data set. So the first row is actually the labels. They are putting it in numbers, so it's easier for them because it's only 10 different types of outputs. And then this is actually the pixels itself. So I know these are all just zeros and then maybe some random values over here. But actually, because this is a grayscale image, let me see where's the end of it. Maybe we need to zoom in a bit more. So we can see that okay, so we can see from down here, right? Counts it's 784. So why is it 784? Because this data set, right, uses images of pixels from 28 by 28 is a square image. So when you times 28 by 28, you can get the value of 784. So this is literally like the values of each pixel in a CSV file. Whereas the first column here, yeah, if I'm not wrong, it should be column, it's the labels itself. Okay, so now that we've seen the data set once, so now we'll go on continue with it. So let's see the images that they have inside. So we can use this train images.shape. So shape shows the dimensions of it. So this is 60,000 images, 22 times 22. So let's see the first let's see the 23rd times 23rd pixel of the image, of the first image. So it has the value of 194. So let's go back to our Excel file. Okay, so let's go to the 23rd. So let me see, where is it? 23rd. Aha, I went too far. Hey, wait, 23rd times 23rd. It's the 500 and the 529. So let's go here, 500. 529. Let's see. It should get the same value. 529. Wait, where is it? Am I looking at the wrong one? Oh well, long story short, you can actually find the value in here, and it's in the, it should be in the first row. So yeah, now we will see the first 10 labels. So first 10 is 9003 027255. So I know we don't understand these numbers. So this is actually the labels for it, and then this is copied from its dataset. So you can search online for CIFA 10. Is it the CIFA? Oh, sorry, the Minis fashion dataset online, and then you can just search for the labels itself. So 9 stands for the 10th one. So the first image is an ankle boot. The second image and third image is a t-shirt or top. The fourth image is a dress, and so on and so forth. So it starts from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Have I run that before? Okay. So now let's see the first image. So the first image is an ankle boot, as you can see from here, 9, ankle boot. So let's look at the second. So yeah, you can see the functionality of notebooks. So it's very easy, just edit like one line and you can run that one block of code itself. So it's easier to debug. So okay, second image is a t-shirt, correct. So that's all. So you can keep on editing this line so you can see like the other images. So now we need to pre-process our data. So normally we'll do some augmentation if a data set is a bit too small, but normally for the most basic, we normally will rescale everything. So why do we want to rescale? So rescaling, like, it's called normalization. So we want to make the values itself as small as possible so that it's easier to calculate for the computer. So big values need a lot of computation, a lot of data, a lot of RAM. So if you're using like small data, so it's easier for them. So we divide by 255. As stated before, why we're using 255 is because every pixel, right, is a byte. A byte is only 256. So we're using 255 here because 0 to 255. So you just divide by 255, and then you can get each individual pixel from 0 to 1. So let's run this. So now we're going to build a model. So we're going to build a sequential model. There's another type of model called a functional model. So functional models are actually more technical and more higher class levels. So we'll be using sequential because they're easier to understand, it's easier to grasp it, because it's just like a flow chart. Whereas for functional, it depends on a lot of type of functions. They call blocks. So that's the reason why we're using sequential. So the first sequential we're going to use, first layer we're going to use flatten. So flatten takes the 28 pixels by 28 pixels, and then you make it into one straight line. So that's each neuron, each input will have one pixel itself. So first input layer, which is the input shape, then we'll dense it up into 128 neurons using ReLU activation. Then finally we use 10. Why we use 10? Because we only have 10 outputs. So that means we have 10 classes here. So we use the 10 classes, and then we use softmax activation. Note that for normally the final activation layer, right, if you have more than a single input, we'll be using softmax functions. So let's run this, and then we'll compile the whole model. So optimizers are here. Normally we use Adam. It's one of the more popular optimizers. And then for loss, we'll be using this type of loss. And the metrics that we're looking at is accuracy. Because normally, right, we'll be looking at accuracy of the model during the training and validation. So we'll know that how good is the model. So now we're going to train the model. So this will be quite fast because it's quite a relatively small data set, and then it's already fully changed into another format. So for training, right, we normally use the function fits. So we'll throw in the images, the labels, and then epochs. What is epochs? So that means see how many times that this whole data set will go through the whole model. So that means they'll see the same data set like 10 times. So at the end of each epoch, you can see that the accuracy is slowly rising from 78%. At the end of it, you'll see it's a 91% accuracy. So that means this model is doing relatively quite good. So now we're going to evaluate. So evaluate means what? It's something like testing it in real life. But for evaluation, right, using the word evaluate, right, the model can see the image as well as the label and then see where is it standing. But this data that has been inserted, right, the model has not seen it before. So this is something new to it. So as you can see, once we run it once, the accuracy is actually 88% only, which is relatively quite low compared to the testing, which we have seen about 10 times already because it's the same data set. You already has memorized some of it. So you can change this epoch. As you can see, the accuracy will go increasing and increasing. And once you reach a certain level, we'll call it overfitting, which means that it memorizes that certain images only. That means if you throw in a new image, right, the accuracy of evaluation or maybe prediction, it will drop all the way down. So there's a fine line between how many epochs do you need for all of this. Let's say over here. So now we're going to predict. So maybe something that has not seen before. So test images, right? It has not seen before. So predictions is like when you're going to apply in real life. So let's predict and then see the first prediction. So it's a 9. So let's see the first image. Let me copy this. So what is the image? Let's try. So you can change this value and then change this value, and then you can see the differences between them. So 9, this should be an ankle boot. So you can see over here, right? It's an ankle boot. Okay, so this is like the first example, the most basic example. So all these examples, right, actually I got it from TensorFlow, their own tutorial. So you actually can go over there. There will be much more in-depth, more coding, all the way to the library itself. So it will be more in-depth and it's much easier to understand to some people who are interested in it. But for some people, maybe you like more basic words, not so technical. So maybe this will be more easier for you. So next, we'll be trying another type of data set called the CFAR data set. So it's also 60,000 images. It'll be 32 times 32 pixels, and it's a color image. So this data set is a bigger data set because it has 10 different classes, and then it is a color image as compared to before that. That is just a grayscale image. So let's load the data set. And then let's split and then normalize and then tell the classes that it is. So let's see the size and the shape of each kind of train and test data. So for training, right, you can see there's 50,000 images. It's 32 times 32 pixels and it's 3. Why is it 3? Because it has RGB. So there's 3 layers over here. So 32 times 32 times 3. This is the data. And then for here, right, these are the labels. So 50,000 labels, same as the images, and then 1, because it's just a string. So it's a single dimension. So it's just the labels. Next, let's look at one of the image. As you can see, you can just change the number over here. So number 8 shows a shape. So let's try maybe like 10. You'll show a deer. I know this is very pixelated, but maybe you can make out like a deer over here. So yeah. So we'll make another class, another model. So let's make another sequential model. As you can see, previously, right, the way we did it was different. Last time we just created a model using this way. So we just add layers on top of it like this with commas, commas, commas. Or you can use another function by Keras by using the add function. So you can see it's quite versatile. So there's many ways of doing it, but I do prefer using the add function because it's easier to maintain for me. So first we'll be using convolutional 2D layers. So 2D means that it'll be a x times y, and then you'll just convolutionize that layer. So and then we'll be using max pooling. So what is max pooling? Max pooling means that from this filter of 2 times 2 image, filter, you'll take the maximum value of that 4 pixels and then take that 1 pixel out as the output. Then after that, you'll go on with the same thing, and then let's just make this model out. The explanation can be seen over here. So let's see the model that we made. So model.summary, this is the function that we use to see the summary of the function. So you can see that first layer is a conv2D, then max pooling 2D, then conv2D, then max pooling 2D, then conv2D. So first layer is a conv2D, max pooling, conv, max pooling, and then conv. So exactly the layers in the way that we want. So you can see exactly how each layer looks like in the machine, in the computer itself. So this is like a summary for all of you to like last minute check what you're going to do with it. So you can see that from depth of our image increases, but the dimension of the image decreases. So this is to make sure it's easier for the computer to understand what we're going to do. So dense layers. So dense layers, right? We're just going to add them in after flattening the whole for this model, and then we're going to see the summary. So you can see, right, from here we have 1, 2, 3, 4, 5 layers, and we added 3 more layers. So 1, 2, 3, 4, 5, then 3 more layers. So this is the previous block, and this is the current block. So they are flattened, dense, and dense. So the output is 10 because we only have 10 classes. So let's compile it, and then this is quite a lengthy step, so I will not go through it. You can see the output there. I've just done it recently. So I've gone through 25 epochs, and then this is the accuracy. So it starts off quite very low, 37%, and then it slowly rises all the way to 97%. However, you can see that this model is not a very good model. Why? Because when we do testing, right, you can see that you only get 50% accuracy, which is very low compared to this one. So that means, number one, we could be doing overfitting, which means that you have maybe too many epochs. Number two, maybe that we have not added enough depth to the whole model here. Maybe we have not enough layers. Maybe we use the wrong type of layers. So these are all trial and error. Although you can see each layer output, so maybe you can optimize your whole model faster. But if you're really lazy, you can just go on. If you have time and you're lazy, just maybe the test run, maybe trial run a few models at the same time, see the outputs of it, then test it out, see whether your accuracy increases or not. So this is another model. Okay, this is a block from VGG. So this VGG model is a quite recent model. You have 2 types of VGG models. VGG 16 was invented in 2019, and then VGG 16 is the model invented in 2016. So these are very recent models, and then this model is quite powerful in recognizing images. So this is how a single block of it. So because VGG, right, is a new model and it uses functional modeling. So this is a single block, and then you add up different types of blocks together, and then you form another type of model using the functional model sequence. So this is just a single block of it. So maybe if you're free afterwards, you can try running this. And once you get an accuracy, you should get about 70%. I will not go through this because it takes quite a long time because the amount of layers, as you can see over here. So the more layers you have and the more data you have, both of them will affect the time needed for you to run the whole model. So what if I'm very lazy to go through it? Maybe I don't want to like create my own model. I don't want to from scratch. So I want to do it quite fast. So maybe you can use pre-trained models. So one good thing about using deep learning, right, is you can use pre-trained models. So pre-trained models, right, is like those models like I said just now, VGG 16. So these are all pre-trained models. They have gone through a lot of images. You have gone through a lot of images, so of course the feature extraction of that model is very good already as compared to this new fresh out of the factory models. So maybe if you use those and then you just do some mini fine tuning on top, like adding just the amount of layers that you want to be your output, then you'll have a much greater accuracy as compared to training from scratch. So I've just said this all just now. So we're using a pre-trained set. So let's import all of this. So the data set, we will just import it as well. So we will manually change the data set to 80% training, 10% testing, and 10% validation. So training data set is usually the bulk of the data set. So normally you will see about 70% training, and then the rest will be testing and validation, or all the way to 90%. So there's 90% training, 5% training, testing and 5% validation. It really depends on you. What do you want to do? Oh, for this example, right, we'll be using the cats versus dogs dataset. So this dataset is actually already installed in TensorFlow, so it's much easier to use. So we will see the first 5 images from the dataset. So this is the first image, second image, third image, and fourth image, and fifth image. So you can see all these images are colored, and then all of them have different amount of pixels. So that means the length and width for all these images are different. So you can see the first one is about 260, I guess, times 350. The second one is 410, maybe, to 320. So as you can see, right, all the pixels have different, all the size of the images are different. So we cannot just like shove it into our model. We need to make sure that all of them are the same width, same length before we can put into the model, because our input size we have already determined in the first layer. So we need to follow the input size. So these are the 5 first images. So now we will do some pre-processing on it. So we will define the function, and then we will say that our image size is actually 160 times 160. We will resize it all of them. So we will change the image into a float type, and then we will divide it by 127.5, which is half of 155 minus 1. So this is another type of pre-processing or normalization. Although I don't really use this one, but yeah, this is from TensorFlow's website, so I'm just following their footsteps. So why we're using map here? Because we want to make sure that all of these images will repeat itself. So it's like a loop function, so we just apply it to all of the train images, the validation images, and the testing images. So now we can see there's new images. So first image is like this, then now the current image is like this. I know it's a bit blurred out, but this is how we don't see, because computers, right, you want to take out features only. So like the outlines of the dog, or maybe this dog has this outline. This is what you want to understand. Whereas we understand from a picture as a whole, they understand as small features. So this is what the computer actually sees. You just want to see the outline, maybe the color differences, the gradients. This is what you want to understand. So this, you can just change the numbers and you can see how many images are at one time. So now we put in this batch size and buffer size. So why do we use batch size and buffer size? It's because let's say your computer is really not up to stuff. So you want to like reduce the memory, because our graphic cards, I know all of us using laptops, most of us using laptops, you have quite limited memory, dedicated memory to your GPU. So this is how we save it, because if the memory is not enough, the whole program will crash and it will not run at all. So this is one way to like reduce the memory. So let's see the images. So we see the first 2 images. So first image is 262 times 350, and it's 3 layers, which is RGB. Then after that, after going through this image pre-processing, you can see that now it's only 160 times 160 and it's 3, and it's the same for all images. So let's say we just take the first 5 images. You can see that from all these different sizes, we all change it to the same size, 160 times 160. So now we want to pick our pre-trained model. So there are a lot of types of pre-trained models. So now we'll be using MobileNet V2. So why are we using MobileNet V2 for this example? Is because one, it's a relatively quite modern model. 2, it's quite light, as in it's meant for mobile devices. It's made by Google for mobile devices. So that means you can do your AI on your mobile. And then number 3 is it has very little parameters. So as you can see from the summary above before, you can see that the amount of param is here. So param depends on the type of layers and then the amount of weightage it has. So this is how many things it has to change per image. So you can see normally we have 356. For this example, right, we only have 356,810 different type of parameters that needs changing every single time it sees a new image. So maybe we can use something that has more than that, but much lesser so that we don't need to waste so much time on training them if we don't need to train them again. But normally for using pre-trained models, right, we will use the same weightage as well, so this is not a problem. So now we will say our image shape is 160 times 160 and then 3 layers. And then we put in our base model, which is MobileNet V2. So our input shape will be this image shape. Include top means that we will be removing the original top layer, which is if I'm not wrong, it detected 1,000 different classes. So the top layer is actually 1,000. But now we're only going to detect cats and dogs. So we only need to use 2. And then this weights equals to ImageNet means that we're using the original weights that was used for the competition. Actually, pre-trained models are normally done in those quite big competitions. So ImageNet won, if I'm not wrong, it won one of the awards at ImageNet's competition. So yeah, you can see from here after running this, this is the model that it is. So it's quite big as compared to what we did just now. So let's see. So there are this many layers. So this is the input layer, and it's like a convolutional batch normalization, value functions, depth-wise, and then it goes on and on and on. So you can see this is just, this is just like the basic, this is what they use for sequential. You can see from here, it's just sequential. Then here is block 1. So this is the functional, and then block 2, block 3, block 4, block 5, and so on and so forth. And you can see it's relatively very big model as compared to what we did just now. So you can see the amount of parameters that it has, it's already very big compared to what we did just now. So what we're going to do is now we're going to freeze the base, because every time you train, you use the function fit, right? It changes all the parameters that it was before. So now we want to freeze the base so that when we are doing the fitting, right, doing the I suddenly forgot the word. Fine-tuning, during the fine-tuning. So when we're training the model for fine-tuning, right, we don't want to change all of these parameters that it was done so hardly by the developers. So we freeze the whole base. So that means none of the parameters can be changed. So you can see from here we have 2223872 parameters that can be trained. So after we freeze the base, you can see that the parameters has become 0. So that means none of these can be changed during our training. So now we put on our classifier, which is just a global average polling. So global average polling is, you take the whole image, 160 times 160 in this example, and then it finds the average of the whole image. And then after that, you put it into a dense, and then we're using dense 1 because you're kind of cheating here. We only have dogs and cats, so we only have 2 classes. So maybe we can cheat a little bit and say that, oh, 0 is one of the label, and then 1 is one of the label. So this is a sort of way of cheating, but it's not really suggested by other developers because this will cause problems later on. So let's just run this. So now we'll combine our base model, which is the MobileNet V2, and then this global average layer, and then our prediction layer, which is the dense layer. And then you can see our summary. So you can see this is the MobileNet V2 whole thing here, the whole model has been simplified. Then this is our pooling, and this is our dense. And you can see that the parameters is just this 1,281 parameters. So now you want to train the model. So actually, what are we doing here? We just want to train these 2 layers. So we're using a learning rate of 0.001. So normally we set the learning rate quite low so that it doesn't like overshoot every single time a new image comes in. So you just want to fine tune it, you want to change it by a little bit every single time. So let's just run this. And you can see that without any fine tuning itself, we will have quite a low accuracy. So maybe let's let it run first. So yeah, we have an accuracy only of 42%, which is very low for with a model with pre-trained model as a base. So maybe you can feed the whole model, do some testing on for the fine-tuning layers. So we just feed it, and then we can just let it run. So you can see after the training process, the accuracy has bumped up to 90%, 97%, and 98% for each round. So I'll not be running this because it runs about for 30 minutes and then it take up quite a lot of time. So you can see from this sample that I just done it just now. And after doing the training, you can see that the accuracy has bumped up to 98%. As compared to before this, it's only 42%, which is very low. It's using the same data sets, but you can see as for the testing, it's using the same thing, but you can see the accuracy has changed quite a lot. So it means that after selecting your pre-trained model, you need to fine-tune it at the top, then only you can start using it. So let's take a break until 11:20, then we'll continue it for the last part. Okay, so I hope all of you are back. So now we'll be using those raw images, because from all of these examples that you've seen before, right? They're all those using all those data sets that have been prepared by other people. Let's say like from those big competitions. Normally they'll be using CSV formats, or be using XML formats, or certain type of COCO formats. Let's say for instance. Whereas for us, like new ones, like we just want to try it out, we just want to play with it. We'll be using raw images for image processing, right? So what if you're going to use raw images? So this is another example. So for UTARians, right, I really do suggest you use your UTAR Google, because as you know, UTAR is using educational Google. So that means our Google Drive is actually unlimited data for storage. So first and foremost, we'll be using images from GitHub. We'll be pulling them and then inserting them into our Google Drive. So we'll be running everything on Google Drive here. So first, we'll connect our Google Collaboratory to Google Drive. So once you run this line of code, you ask you to go to this URL. So just press on it, then select your UTAR account. Then you just allow it, and then you just copy this link. After copying this link, you just insert it. I don't think there's a paste cell, so you have to Control V into it, and you just press enter. So let it run for a while, and then you will see it after this whole thing is finished processing, because it's just authorization code. So that means every time you rerun this whole program, let's say you close it, you close this Google Collaboratory, then you open it again, you have to do this process again. So once it's done, you'll see it's mounted at content/G drive. So you can actually see from here, just now you only saw that there was only sample data. Now there's also G drive. So that means it's connected to sample data, which is this disk, and you also connected to the G drive, which is your Google Drive that you have connected here. So now we're going to use some Linux terms over here. So CD means change directory. So we're going to change from G drive itself to my drive. So you can see now we're in the content/G drive/my drive folder. Now we're going to use this ls function. ls stands for listing. So we're going to list the amount of files or folders that I have in my drive. So you can see it's collab notebook, FYP, blah blah blah, a lot of other stuff down here. Oh wait, I have some technical issue. Wait a minute, let me delete some stuff. Sorry, because yesterday I just ran this and I forgot to delete the original file for this tutorial. So once you run it again, you can see it's just say it's mounted already. Then you just change directory and then list again. So you can see down here, right? It's just all my files over here. Please ignore the ones that are sensitive. I believe in you guys. So fun fact is, when you're doing listing, right, you can see it's a folder when you have this quotation marks, or maybe it's a PDF. But normally it will just come in this format without any quotations. So now we are doing something more close to Python again. So OS is just checking if the OS system is a library. So OS path is directory. Is there a directory here? If there is a my Keras _dl, then you will make this directory. So mkdir means make directory. So you'll make a directory called my Keras dl. If it's true, that means this folder exists, then this whole thing will not run. So let's say I run this thing, you shouldn't have any output, but you'll create a directory. So now we can try it again. Just show. Okay, so you can see from here, right? Down here, I don't have any my Keras _dl. But down here, you can see there's a my Keras _dl folder. And then now we'll change the directory into that folder. And you can see that folder is actually empty because there's nothing over here. There's no output from the listing. So now we're going to say because this folder name is actually from the GitHub, and then this GitHub is actually done by me. So it's kind of empty in it. Then there's a bit of coding error somewhere, but it's still usable. So we'll just run with it first. So we'll be using GitHub, and then we will clone it. So that means we'll be copying the files in GitHub, and then we will paste it in our Google Drive. So these are the clone and pull functions. So this is the link to the website. Actually, you can follow the link and see it, if I'm not wrong. Let me check. Yeah, you can open it, and then you can see that there's a folder called, there's a few folders inside. So we'll just run this, and then you'll pull it, and then you see cloning into Keras Workshop, and then you'll copy and paste everything in it automatically for you quite fast. Because the main reason we're using GitHub is because we don't need to slowly upload, because not everybody's internet at home I know is up to speed, which with the current need of fast and uploading and downloading. So you can use GitHub, which is much faster. So once it's done, you can see it's back to a play button. And you can see there's a folder called Keras Workshop, and we change in that folder, and then list it, and then blah blah blah. It's the same function. So you just want to go to this base folder. As you can see over here, right? Actually, if you know the directory well, like from here, you can check. Okay, so where are you? My Keras DL. My Keras Workshop. Ta-da! So you can see it's all in here. So actually, if you're really lazy, instead of going through like one by one, CD, LS, CD, LS, CD, LS, so actually from here, after you have cloned it, you can actually CD all the way to this. So you don't need to go through these two extra steps. You can go from here to here. So I'm now going to list all the images that I have in the dataset. So this dataset is actually not very big. It's just a few thousand images, if I'm not wrong. Yes, it's just a few thousand. So this dataset actually composed of 4 classes, as you can see from the file name. So we have healthy apples, we have unhealthy apples with black rods disease, and then unhealthy apples with rust disease, and unhealthy apples with scab disease. So now that we know all this data is in our Google Drive, right? So we can start doing it. So only for using notebooks, right? You need to define the TensorFlow version, especially for Google Collaboratory, because there's a lot of type of TensorFlow version. So we're using 2.0 because we want to use Keras. So if you're using like Jupyter Notebook, right? Jupyter Notebook actually depend on the software, the drives that you have downloaded and installed into your hardware. So that is okay, but we're using Google Collaboratory, so you just want to mention that we're using 2.0. And then we're importing all of these type of libraries. So TensorFlow, STF, TensorFlow datasets, OS, random, glob, shuttle, numpy, blah blah blah, all this. So yeah. So this actually is just for plotting graphs for training and validation and versus epochs and confusion matrix. So I'll just go through these two quite briefly because this one you can just get it from anywhere on the internet. So this is just an X to Y graph, and then you'll be just comparing epoch versus accuracy or epoch versus loss. That's all. And you can just get it online. The power of internet these days. So confusion matrix, I know by the time you're listening to this, you're already confused. So I will not talk about this, although, and this you can get it from internet as well. There are shorter versions, but I prefer this one because I like the color. And this we will be able to see afterwards, so I'll be explaining more on the confusion matrix afterwards. So we just run this, so you can define all of these functions. So now we're looking at our data set. So we know our data sets is just apples, apple scap, apple blackboard, and apple rust. These I'm just calling it. Actually, you can just define it by yourself or any way because there's no predetermined order because we are making it ourselves. So this is no predetermined orders. It's not like those examples that you have online where they already have labeled for you. These are all non-labeled, just clear, clean cut images. So it's up to you. Everything is up to you. Whereas for this data set, if you're using this format, right, you have to follow this number has to follow it. So let's say, because I already calculated, I have 1,645 images of apples, 630 images of scaps, 621 of black rods, and 275 of rust. So as you can see on the data set, right, this data set is actually quite biased in a way. How to say so? You can see that the images, right, are all different values. We have those in 1600s compared to close to 300. We just assume it's 300. So how many times of this healthy apple is it compared to rust? So that means the whole model will be leaning more, the output is always leaning more towards the healthy apples. So actually this is not a very good practice, but for the sake of examples, we will just go with the flow. For those people who are professionals, please do not hate me, thank you. I know you will. Okay, so now we're going to change everything into 160 because I'm going to use mobile net afterwards. So I'm just going to follow as the example before, 160 times 160 times 3. So this is just a way to calculate my distribution of the data set. So I'm going to use 75, 15, and 10. So this is just a way of calculating every single one of the data set, how many I need to pull out. So let's just run this. And then now this is actually looks confusing, but actually it's just the same thing. It's just repeating itself again and again and again. So now we'll change the directory into this directory. So you'll check if train/apple is around. If it's not, you run all of this. So you make directories. So you run train test valid, train valid test, train valid test, but it's all different type of class because we are going to use 4 classes. So you can see there's 4 big blocks here, and then each of the block they must have a train, valid, and testing because we're going to use train, valid, and testing at the same time. So I'm just going to make all these directories, and then after that I'm going to move the files. So glob is a way of moving files. So it's just randomly selecting images from there that has the name file name as healthy. So it doesn't care what does it have behind it, so long it's healthy because there's a style here. So it's just healthy anything. It can be just 1 or no number, so long it's just healthy. It doesn't care in what format as well. So it's just healthy, so long as this name, you move it. So sizes is this one. So how much you want to move is already predetermined from this function above. So it's just 0 means that it's all the healthy apples that I've selected before. 0, 1, 2 at the behind is just for testing, validation, training, validation, and testing. So this is just another way of writing it, although it's more confusing, but it's more pleasing to your eyes, so I just pick this way. So you just move everything into the folders. So after running this, right, you can see that it's actually much lesser after we list it out. So this goes on for the same for all of them. And then now we want to show that all the paths, the training paths, the valid paths, and the testing paths are actually just this /train. Because in training, right, you can see that there's train /apparat. So that means in training itself, there's more subfolders, which is 4 folders from here. So now you can list it out. You can see that these are the things that we didn't use, just 1, 2, 3, 5 images. And then we have 3 folders, test, train, valid. And then if we change, let's say, sorry. Let's change into, let me see, where were we just now? We were in the workshop dataset folder. So you can see from here, let's go into test. Okay, yeah, let's go into test and then we can list it out. So you can see in the testing for in the testing folder, there are 4 different folders. So let's change into one of them to see the amount of images. So you can see we have changed into the AppleSCAP testing folder. And you can see that these are all the images that they have inside it. Or actually can go to the Google Drive and slowly wait for it. But I found out that Google Drive actually updates very slowly. So this is a much faster way of doing it. Although you don't really see the images. So now we're going to do some pre-processing on all the images. So we're going to use this rescaling using this function. So we're just going to divide by 225. And then flow from directory means that it's going to use this directory and then this target size, and then the data set is the classes. So for training and validation, normally we do use shuffling. Why? Because we don't want the model to memorize the order of the images that come in. So normally we will shuffle it up and then we just let it try to do it by itself. Whereas for testing, right, because it has never seen it before, so normally we'll turn off shuffling so that we can see it's easier for us as the programmers to do it. So we can see that, okay, first image, because maybe we have done it a lot of times, we have already memorized the order for ourselves. So it's easier for us to debug, but if you want to turn this off, it's okay for you also. So you can see after running this, you can see that there are 276 images in 4 classes for the test, and this is for validation and this is for testing. So now we are going to create a path for the place to save the model. So because we're using Keras, right, we can use .h5 type of file format. So .h5, right, not only saves the architecture of the model, you also can save the weights and biases, which is quite good, but you're limited to using Keras only. But I'll say it's well, the benefits are better than the, the benefits are better. So maybe you just use .h file, it's easier for you. So now we're going to use our base model. So I already taken in MobileNet v2 and then I'll send it to false so we can train it. Then you'll see the model itself. So this is the model. And then we'll create fine tuning on top. So I'm going to add, from the sequential model, I'm going to add the base model. Then I'm going to add another global average pooling. And then I'm going to add dense. But this time I'm going to use 4 instead of 1. Because you know, just now in the example above, we use 1 only because we only have 2 classes. Here we can cheat. But here we're using 4 different classes, so we can't really cheat. And then we'll be using softmax because we have more than 1 neuron. So let's just run this. And then see our summary. So you can see it's the MobileNet v2 and then pooling on top, then dense. So you can see we have 5,124 parameters that we need to look at every time there's a new image. So let's just compile this thing with different type of losses and optimizers. So just run the model. So you can see that I'm using 64 steps per epoch, and then there will be 10 epochs only. So and then I'm giving it training, data, and I'm going to give it validation data. So you can see from here, I'm not sure you can see it or not. So the accuracy is actually starting from 31%. That means the model doesn't really understand what we're looking at. Then it slowly goes up all the way to 94%. And then our accuracy for validation actually is from 60%, which is much higher, to 90%, 91%. So this actually, by using just accuracy and validation accuracy, right? It tests accuracy and validation accuracy. You can see whether your model is actually being overfitted or not. A rule of thumb is that the accuracy has to be lower than the validation. Sorry, it must be higher by a bit only. So, oh, sorry. It run for about 10 minutes, so I'm just going to cancel it first. So after running that, then you can see your plotting. So I plot here already. So you can see from the example before I ran it, you can see the accuracy actually grows up all the way to 90+%. For the validation, it goes from 60% all the way to about close to 90%. Then for the loss, it goes down all the way to 0.2. So yeah. Now we're going to set the whole model to not be able to train, because we just want to make sure, we're just assuming that this is our final model. So we're going to set the whole model to not train. So actually this step is optional. You cannot want to do it, but I just do it for personal reasons. I like to do it. And then now we can test it. So as you know just now, right, we only use the validation data and the training data. So now we're going to use the testing data. So after running the predictions, so you can see it's model.predicts. That means that it's going to predict itself. So and now we're going to look at the confusion matrix. So this confusion matrix is going to call the function above that we have defined. And you can see that the confusion matrix, oh, I think this is wrong. Oh, because I didn't run this thing all the way, so the confusion matrix is kind of off. Let's just run this one, and then while I talk, let's wait, because it ran for about 10 minutes. So I'll explain confusion matrix first. So confusion matrix is just a true label versus a predicted label. So what is true label? True label is the correct label that we have sent into the model. So let's say we have 4 models, right? Apple, healthy apple, apple with scab, apple with black rot, and apple with rust. So this is the true labels. That means these are the correct labels that it should be predicting. And these predicted label are the labels that the model has predicted. So for example, with this wrong confusion matrix, there are 85 healthy apples that has predicted correctly. Only 1 apple with scab is predicted correctly, 1 for black rot, and 1 for apple rust. So for confusion matrix, right, once you look at it, you can see how good is your model at a glance. Just look at it diagonally. The rest over here are all wrongs. So yeah. Oh, it's still on the second epoch. So you can see it's kind of slow. So once you're done with that, you can save your model. So just now, remember I talked about the .h5 file. So you can save it into your Google Drive, and then you can download it, and then you can use it on other devices, so without training again. So it's practically like the final product that you have done. So I've saved it into this model, and then after that, I've loaded it again just to make sure that this is the correct model that I've saved. So this new model, right, actually is more done on the new device. So you use the load model function. So just put in the model path, and then just load the model. And then you just put in a summary to check whether your model is correct. Oh, it's still running. Okay, so while it's still running, and then we still have a little bit more time, so I'll open up for some Q&A. Any questions? Okay, so I guess there's no questions. So we're waiting for this one to finish. I hope it can finish soon. I'll just run all of this in advance first. Okay, you can see that the graph is out again. And now it's making predictions. So you can see that from the confusion matrix, right, the model is doing much better with 162 versus 53 and 60 and 24 correct. Whereas there's only like these few errors like 1, 2, 3, 4, plus 8, 12, 16, 17, 18, 19. So there's only 19 errors out of that few hundreds. So it's doing very well. And then I'm going to save it and then going to load it again. So you can see it's exactly the same thing. So, okay, so that's all for today's workshop. Thank you all for joining. So before you leave, please fill in the sign out form for UTARians. And then for everybody, please do fill in the survey form. Thank you very much.